well, some list of questions to kick off this discussion. The way that I look at the lineup, we mostly have a bunch of theorists on the call, except maybe for Peter. But I'm gonna be like mostly directing my, I'm gonna also like put on my learning theorist hat as well, just showing out this cold water bottle instead of the NoRIP swag that everybody's so proud about. So yeah, from the theorist perspective, what I see is that there are so many new algorithms that are being introduced in these past couple of years, and everybody has their own favorite words and terminology to talk about them. And this is, I think, sort of giving theorists a bit of a bad name, right? So if you just read all these papers and if you just talk about these kind of exponential weights policies that, well, we have heard Nevena call it polytext or AAPI before. Mathieu was calling it regularized policy iteration. Yesterday, Alec was calling it natural policy gradients. So it seems like a little confusing, and it's a little difficult to approach this kind of literature if these things keep happening. So I just really wonder, like, well, who's responsible for this? What can we do about this? How can we better communicate these results? Because eventually we want people to read these papers and understand them and take away the big messages from them. None really seem to like this question, but.
It's kind of a tricky question because like all these things are like they're very similar, but they're all like slightly different. And so like with the different names, we just like sort of denote like the subtle differences. Yeah, there's also MDPO, and there's all these things. I don't know what the solution is.
Also the same deal.
Yeah, and I think it's not specific to reinforcement learning. When you look at the online optimization literatures, you have many algorithms that are known under different names. If you look mirror descent, FTRL, multiplicative weighted weights, these names are not from reinforcement learning. They come from different fields, and we took a name. So the other fields are responsible.
Yeah, so what I'm dreaming about is something that has happened in the online learning literature in the past decade or so. Before, everything was a complete mess, and there were like a bunch of different algorithms floating around, and there was like no unified terminology, but then everybody converged to just calling it mirror descent and follow the regularized leader. So do you think that this is ever going to happen in reinforcement learning, in particular in theory?
Well, so at least we had only one online learning problem, right? Everybody agreed that we have an objective, which is regret, first of all. So for everything, you have the discounted version and the finite horizon version and the average reward version, and they all have their certain differences. So we can't, like Nevena was saying, they all result in slight changes to the what the algorithms have to do, and so I don't know if it's as clean necessarily. In a way, the reason I kind of like making that's why we decided to, in some sense, adopt the NPG-like terminology, because it was kind of maybe going to the earliest algorithm with that structure that we could land on. So kind of going to maybe the older terminology in that sense. But I think in other cases there are really, like, okay, when Matthew is playing around with other regularizers, it wouldn't be fair to put it within the same nomenclature anymore, right? So yes, it could be that, of course, when we get broader kind of unification of many of these, really in a way that everything becomes a special case of something, we can maybe unify better.
Right. Yeah. So I guess like another thing that that bothers me a little bit on this front is like, what is the definition of policy gradient algorithms in the first place? Because right now, if you read in particular deep RL papers. Somebody says that they did the policy gradient algorithm. Usually for me, policy gradient means that you're using the policy gradient to estimate the gradient of the average reward objective. But apparently for a lot of people, it just means that you're just taking the gradient of some policy parameterization at some point in your algorithm. So I just really wonder, like, what's a remedy? How can we speak up? What is the right forum to make noise about this? What can we do about this as theorists?
This is such a hard question, Gergely. I wonder.
Yeah, I know.
I wonder if someone needs to write a theory book that puts together all this nice terminology and makes this nice and clear. Hint, Gergely, maybe you'd like to do something like that. I think it's probably true that when Rich wrote the textbook, that it really helped make the field have a unified terminology. It's hard for any single paper, I think, to cause a unified terminology. I agree with your point about policy gradient. That term is just really super unclear.
Right, yeah, maybe secretly I'm looking for co-authors of this book right now in this call.
But actually, maybe the way you're seeing it because you're contrasting with online learning. I don't feel like RL is that terrible for terminology. Or maybe that it's not holding things back too much, nor do I think theorists have a bad name because of it. At least I've never heard anyone say anything.
Oh, well, I guess another thing is like actor-critic algorithms. What does that really mean in the same way? Q-learning, what does that really mean? Is it like the stochastic approximation algorithm or deep Q-learning, DQN? The DQN algorithm doesn't even have a name. So that is another bit of source of a confusion. But I guess from the other perspective, the question would be that so if somebody is coming from the practical side and they want to get like a better theoretical understanding of their algorithm, like from the theoretical perspective, what can we suggest to them? Like how should they phrase their questions, and how can we like direct their attention to like, hey, this is actually the part of your algorithm that somehow should be amenable to theoretical analysis. How can you reach out to this point? Well, I guess for me, so I didn't ask this question during Peter's talk, but maybe I can ask it right now. Is in your weighted Bauman error definition, Peter, you had these weights and you had this definition, you had this kind of heuristic for weighting. There, well, my question would have been, okay, so how do you picture, just go back to the tabular case, and in that setting, what would be the ideal weights? What would those look like in the first place? So if you can answer this question, or at least this is how I think as a theorist, then you can branch out from there and start to understand your algorithm in more general terms.
Yeah, I like that suggestion. I think going back to tabular would make it a lot easier to work out what might be optimal there. I mean, easier. I don't know if it'd be easy in the absolute, but definitely easier. Yeah, top of my head, not sure what it would look like, but I like that kind of question. Yeah, what would it look like in a tabular case?
Is this usually part of your workflow, or when you come up with algorithms, you start from a different perspective? Just look at the loss function and try to like figure out how to adjust this in a way that is amenable to just gradient.
Yeah, in this case, the way this came about is essentially it just seemed like, using the min or swapping the max and the argmax seemed just that it was losing a lot of signal. That was really the starting point. And then let's see what else we can do. Well, ideally we'd have some kind of Bayesian style loss function that weights every piece of information by how much you can trust it, and then things should work. And then we went to weighting by 1 over the variance, with a Gaussian assumption in the loss, right? But that just didn't really work. And I think a reasonable step could have been to go to what's the simplest case where we can actually work it out and see what it yields us. Instead, we said, hey, this doesn't work, seems kind of unstable. What can we do to keep this more bounded? And sigmoid will keep it nicely bounded, and it just worked. And then we ran with it.
So I understand the specifics here, but I guess my more general question here is that Well, how far do you think that this approach can be pushed of just, experiencing some problem with your experiments, right? You just see something pop up and then just go back to your loss function and try to adjust this. Do you think that everything can be solved with this pipeline in reinforcement learning? Because this is a bit of a provocative question.
Yeah, it's, I mean, definitely not in the sense that it completely ignores exploration, which probably needs to be solved in a very different way than just adjusting a loss function, or it's a very complicated loss function maybe.
Yeah, right. And I suppose
if I can jump in on this, because I think I want to also answer that question. Let me take this into maybe controversial territory, Gerger, as well. I think if you do DeepRL on the practical side, there's actually a lot of issues that aren't being looked at from the theory side at all, right? We talked earlier about the fact that a gradient step has a cost, and it has a very sort of practical cost that when you implement your algorithm, you have to think about that gradient step. And so I wonder if in this context, it's also sort of reflective of that, and this is maybe my challenge here, is the theory addressing the practical questions, or are there lots of questions that we should be thinking about that just aren't being surfaced right now? I don't know, Peter, if you would agree with me on this, that there's this extra layer of stuff that doesn't get theorized at all, if that makes sense.
Yeah, so I think maybe one extra layer here is just a sociological layer, which is different students, different postdocs have very different flavors of things that they like to work on, right? And I think that often has a lot more influence on exactly how the path goes than maybe what is, maybe the most rational, senses. But so to Mark's point, I think often there are things where at a high level intuition goes unused. And then you can put together an algorithm that intuitively makes sense and works pretty well, like what we did in this case, and yet lends itself to maybe a much more careful version of it in the future. And I think there's, in some sense, the question, does it all need to happen in one paper? Maybe it's okay to first put out a paper where it captures most of the intuition and it shows sign of life that if you capture the intuition, you can really get something. And maybe there's another stage where, another paper or two get written that really carefully go in and say, okay, well, actually, if you do it this way, you can get even more signal and you can prove this and this about it. And I think it's often different people who like to do those two types of work. And I think that's a big part of the dynamic. And in fact, I think that's great. And I feel like that's where, new work gets generated, I guess.
Right, yeah. So I guess like one tricky thing about reinforcement learning is that not everything that makes intuitive sense actually works, right? So like one specific instance of this is of course this double sampling issue that Martha was mentioning as well, and this Bauman error issue. Just write down this Bauman error, you just want to minimize it, you just replace all the expectations by samples, and then a lot of people would expect that to work, right? But of course it doesn't work. And you need to introduce like further tricks like this saddle point formulations or various other tricks, which I guess like leads me to like a variant of my question that I was trying to ask before, is that do we think that everything can be reduced to convex optimization and gradient descent in reinforcement learning, or are we going to need some more tools, or are we going to need some more theoretically motivated ideas for things to work better?
I'm sure other people have an answer to this question. I'm kind of wondering if maybe we are. So what's the one thing that I think we probably will need to do? We'll need to understand what's sort of the dynamics of our learning systems. But I wonder if that's going to have to be restricted to convex losses and exactly using gradient descent. We could imagine analyzing other types of updates that are not strictly gradient descent updates, but that we could characterize in some way that converge to good places and are stable and so on. So I'm kind of looking forward to a time where we can look beyond just here's my objective, here's a gradient, and think about what are other ways I could move towards a good solution, but taking, say, a different path that isn't obviously a gradient path. I mean, arguably the gradient correction methods are actually exactly this, because they aren't gradient methods, but they are still a reasonable dynamical system that has good properties and gets to a good solution.
Yes, and you can certainly see these ideas pop up in a lot of theory papers, but then again, I guess my issue is that somehow this doesn't seem to go through to the more empirical deep RL papers. And I guess I'm just back to this question is, okay, how can we publicize these results better? How can we tell more people about double sampling? How can we tell more people about these gradient corrections and help people be educated better?
It's a good question. Yeah, I someone else probably wants to say something, but I kind of like what Amir Masood said here. Do you mind if I repeat out loud what Amir Masood wrote? Because I'm not sure if everyone can see it when it says to all panelists.
Yeah, maybe you should speak up, no? Amir Masood, go ahead.
Okay, so I guess it's kind of like maybe cynical viewpoint. If we start from, say, basically, well, the way I see RL is mostly starting from MDP, knowing the model, and then we gradually approximate things. And in MDP literature, basically, we can categorize the number of methods in few categories. I mean, value iteration, policy iteration. You can argue that both of them are variation of modified policy iteration. Maybe policy gradient, which is a softened policy iteration, and linear programming. And then many other methods are kind of various approximation of it. So sometimes I wonder, have we missed any kind of big class of methods that are very different from any of them, which might exist, I mean, in theory, and work very well? Of course, I mean, it's difficult to answer because if we knew it, it wouldn't be missed. But when I go back to kind of the theory of, or why we have these value iteration, or something like value iteration, it somehow seems a bit, well, not arbitrary, but just one solution that seems that, say, maybe Bellman thought about it and sounds reasonable because he knew something about, I don't know, fixed point iteration of operators, and then he applied it and everything worked. Is there anything that we need to know, or we can discover that, or you feel that might be there, but we don't know?
Yes, I totally agree.
I even think we can go further by saying, is the Markov decision process a good formalism for reinforcement learning?
Can you say that again? Sorry, you're cutting out a bit.
I'm saying that we can even go further on asking if Markov decision processes is a good formalism for reinforcement learning.
Well, have we managed to solve Markov decision processes? Is that what you're?
No, but having something else. I agree with the point of view of Amir, but yeah, most of the things are variation of policy iteration, value iteration, or linear programming. Some parts of dynamic programming were not studied that much, like linear programming was not considered from a practical viewpoint for a while it's a nice theoretical work, and it has been recently somehow revived by the DICE framework that Leon could talk about this, and it can create a new body of literature, I think, really. But maybe having something else than LP or PI or BI will require having a different formalism than Markov decision processes. And there are some alternatives. You have inference as control, control as a probabilistic inference. You have the linear MDPs, the one from Tabular, and a few other things. But yeah, it's a hard question. But I think that's still so much to do with MDPs too. And also regarding the practical empirical thing and the theoretical thing, I think it's a go and back stuff, because I think many, I don't know how many, but there are deep learning algorithms, deep reinforcement learning algorithms that have been produced by people coming from deep learning, and not necessarily with a big background on reinforcement learning or on its theory, but they came with some ideas that maybe made no sense from a reinforcement learning point of view at the first sight. And then thinking about it, it was indeed a very clever thing, and you can say things theoretically. So I really think it's a go and back stuff that is important, and it's not specific to reinforcement learning. If you do math and physics, it's the same story. And the last thing about the unification of theory, it's not that's the same as you said before. I mean, polytext is not the same as regularized value iteration and so on. Look in the details. So if we call all these different approaches the same name, maybe we could lose something. And by trying to ground everything in the theory, we might miss some opportunity to do better things, to give new ideas for the theory and so on.
If I can jump in on this also, Gergely. I think there is an opportunity to what did you say, educate or bring new algorithms to the table through open source software. And it's probably easier to do than it used to be, right? And actually, in fact, a lot of the tools that people end up using are based on what is my neighbor using, and what is the open source package that I can the most easily download, and what programming language do I feel comfortable with. I wonder if there's an opportunity here to say, hey, some of these algorithms are actually fairly easy to implement. Let's add them to open source packages. For example, why not dopamine? And maybe if they aren't, then that's a sign that something else needs to happen in terms of how do you actually get this to be implemented.
Yes, that's right. That's a great point. Like usually when there's this final year project in my reinforcement learning course, I see many of the same lines of code popping up from certain code bases. So I very much agree that the ideas that end up winning are the ones that are easily accessible in open source software.
I mean, I think the case was made for UCT a long time ago, right? That UCT sort of prevailed as a search algorithm for many of these domains because it was both easily implemented and actually robust to implementation errors. So maybe the same applies to RL algorithms.
Right. So stop proving theorems and start coding.
Nevina, sorry, I interrupted you.
Maybe not going that far. I think it's interesting to look at the open source code when it's available, because you have some very efficient algorithms that are sold in the paper away, and it's not the reason for why the algorithm work. And maybe I'm not saying that it's willingly, but maybe it's easier to sell some fancy theory while the core reason for the algorithm to work is different. And so reading the code can be helpful. It would be better to have it in the paper, but some very smart things are not in the paper or not done in the code. So I think even for storation, looking at the code is useful.
Yes, I agree. So I think Nevena wanted to say something.
I was going to say the exact same thing as Matthew. Like, it's not really like the vanilla version of the algorithm that makes it work. It's all the tricks in the code. So yeah, it's a whole other can of worms.
Is that true of your algorithm too?
Well, we only implemented things on like simple cases like tabular and linear. And actually everything is implemented exactly except for like API. In the linear case, we had to kind of approximate the Boltzmann temperature. But like if we implemented it with neural networks, I imagine maybe we would need like a bunch more tricks to make it work.
This is an interesting point. I wonder if there could be several reasons. One is that optimization is not done well enough with neural networks. Another is that could be that are we looking at the right objective function? If you look at papers, for example, the 2009 TD2 GTD2 paper, there are several options and there are more objective functions these years. Which one is the right one? I think it's not clear to me. I'm curious what people think about the right objective function for RL. It's for value function approximation, not Poisson gradient. Poisson gradient is relatively clear.
Okay, so Li-Hong, you're saying you're not sure what the right objective is because there's so many out there, or because we don't know how we should trade off function approximation resources, or what? Maybe say more.
Yeah,
Yeah,
so I think I'm sort of getting what Li Hong is getting at. Like, there are like so many out there. We don't know, if optimizing one is better than the other. And it would be nice to understand, like, if I want to do like policy evaluation with this and this function class, what is the objective for me to optimize? As you were saying, Martha, right? That, if you have a linear function class, then of course you should be optimizing the projected Bauman error. If I have something else, then what the hell do I do? Where and how do I start? Am I just going to take the usual DQN objective and optimize that? Or can I do something more clever?
I agree, and we can even frame this as, if you look at supervised learning, for example, classification, you don't optimize for the accuracy directly because there are good reasons for not doing this. And you optimize for proxy. And in reinforcement learning, even if we know the good objective function that is maximizing the value, we're not really using that much proxies, but it's more difficult. So what will be the hinge loss or the cross-entropy loss of reinforcement learning? I think it's an interesting direction of research.
Yes, this is one of my other hobby horses as well. It's like, well, why the Bauman error and why the squared Bauman error? So we know that, of course, that the optimal solution, the Bauman error is 0. And of course, if you square it, it's still 0. But why are we using this particular distance metric? And why not something completely different? Does anybody have like a better candidate for this?
Yeah, in a sense, these objectives are not arbitrary. They're consistent in the sense that if you make them completely 0, you get the optimal policy or solution. But when suboptimality is unavoidable, then are they still good candidates or proxies? I think that's the question.
Yes, sure. I mean, you can come up with other objective functions that are going to be, 0 when you have the optimal policy, just the same.
So I guess the question is, how would we answer this question? Like, how would we know that we have the right objective function? Or how could we tell the world, here's the objective function we should use? So Li Hong, are you imagining that we should have an answer to this question, or that we should be doing way more experiments across settings, what works well, or the theory should tell us, this is the right choice?
Yeah, well, I suppose that just because we managed to show upper bounds for a certain loss function doesn't mean that that is the ultimate answer. Maybe there's something better.
Let me add something to this, actually, because I was having a conversation with a good colleague of mine here at McGill, who was in mathematics, and we were talking about deep reinforcement learning, and he was very surprised that we were finding solutions that, while we start from the Bellman equation, we end up with a solution that does not actually satisfy an equation, right? Because you have function approximation errors, and so it means you have everywhere your equation is not being satisfied. And I mean, in practice, we actually see this in the sense that when we use TD methods, we find very different solution concepts than when we use residual gradient methods. And I think that's why TD methods tend to work better. They're doing something different. They're trading off these things differently. But to me, that's also saying we have these massive blinders if we start from the Bellman equation and pretend we're solving it, because we're actually not solving it. We're doing something completely different. And so the 0 error case is not the right one to look at all, if that makes sense.
Yes, it makes perfect sense. Like if you look at the DQN objective, or if you look at Q-learning, it's usually not even sure if it has a fixed point, right? You need to make some very, very strong assumptions, and there are known counterexamples in which it doesn't have anything. So you probably need some better formulations for this.
So Li Hong, do you think that these approximations to the Bellman error are not the right objective function?
I'm not sure. That's why I asked.
I feel like it's sort of, there's a hopeful thing right now where we don't know the answer to this question yet, but I feel like we're well poised now to start answering the question. Like all these recent developments, I think are going to help us both test things empirically to sort of guide like what looks like it's the most promising empirically. And then maybe, I mean, there's a lot of nice theory that's happening right now. Non seems to be just producing a bunch of different things. Maybe we'll see some theory telling us too. Maybe, but I guess what I'm saying is maybe we will get an answer to this question, but it's just a tad too early.
Right.
Yeah,
In a sense, So in the end of the day, if we agree that RL is about maximizing reward, then perhaps reward maximization is the real objective that we really care about. I think now the missing link is the connecting value function error to the reward maximization objective. We have some bound there, but the bounds are perhaps a little bit too loose to be meaningful.
I mean, to me, so I think I totally agree with this maybe potentially very loose link between Bellman equation and the optimal optimal policy or the correct value function, right? But I think, to me personally, that the reason to use Bellman equation is mainly for the off policy or even the fully offline batch setting, where you just don't have too much more choice. Or where in the online setting, you can afford to do much more and do things that are very different. And in the offline setting, and it is very nice that Martha mentioned the double sampling difficulty. I'll just say some quick technical things, like instead of the squared Bellman error, and in recent years, I've found personally like being very much attracted by what I've been calling like average Bellman error, where you just average all the Bellman errors across different state actions like together, but using different weighting functions, right? So that's, I think, a very nice other way to resolve the double sampling difficulty, because when you take the marginal expectation over a whole distribution, your double sampling difficulty like automatically goes away. But I agree, like it still takes, I mean, we're mainly investigating this approach like pretty much in an early stage, and we still need time and empirical evidence to tell us whether this is truly promising or not.
I think, Li-Hong, you bring up a really good point that whenever we do value estimation, we're usually imagining it's in service to control, and we're not somehow directly optimizing for the control performance when we do value estimation. But I will say that some cases people actually just want to do value estimation, very small number of cases. It is actually possible you might want to estimate values. And then there we might actually want to understand what's the best objective for this easier question, which is how accurate can my values be? And then maybe we shouldn't even be learning values if we're doing control. I don't know.
Right.
I want to put one other thing out there in terms of objective, which is minimizing the amount of human interaction required to completion. So let's say if you train AlphaGo 0, no human interaction required. You just run it and you're done. But for many practical problems, maybe the reward has to come from a person, and they can give different kinds of rewards and how much attention they have to pay to the whole thing. And you can actually start thinking about very, very different problems at that point. You start thinking about, okay, what if I try to model the human? How accurately do I need to model the human's feedback mechanism to be able to keep learning? And when do I need to go back to human? And so it's a different kind of sample complexity where you only count human interaction time and not simulator time.
Right, and you have some constraints on the training procedure itself rather than on the final policy that you want to output. You don't want to have tragic disasters during the training procedure.
No disasters of safety, or it could just be efficiency. It could just be you want something trained. You want it trained, and you want to spend minimal time on it as the human designer or somebody you hire to spend time with it. But you consider samples free essentially, which I think is very uncommon right now. But you can in principle consider samples free as long as there's no human involved. That setting is quite interesting too.
Right, and it feels to me that it's very difficult to start from a dynamic programming perspective and design an algorithm that respects these kind of constraints.
So definitely need some more layers, yeah.
So maybe I just add something about kind of this discussion about the Bellman error. I guess that's true. Like it is upper bound of what we want. So it's a surrogate kind of objective, which may not necessarily be the best thing. But I think we can divide kind of the question to two parts. One is that whether there are other objectives, surrogate objectives that are easy to kind of compute other than Bellman, some norm of Bellman residual. And then the other is that if we restrict ourselves to Bellman residual, or then some norm of Bellman residual, what norm is the right one? And usually we use some form of L2 with respect to some measure. And even if we restrict to that case, I guess it is not obvious what measure it should be. especially if we want to think about the case of control, because it doesn't necessarily mean that if we make some error in this region of state space, in the future, after a few iterations of, say, policy improvement, we are still, what would be the effect of that? And I think we have these kind of error propagation results that show how these errors propagate. I think the problem with most of them is that it is difficult to compute them. So we can't know a priori what is the right norm, essentially, or right measure.
Yes, right. There are so many different ways in reinforcement learning when we talk about how to acquire samples. And well, there's a lot of work, empirical work, that uses replay buffers, whereas it's very rare to see theoretical studies considering this. Most of the theory is about like minimizing sample complexity or regret or these kind of notions. But this is not what happens in the most spectacular applications of deep RL, right? There you always have some kind of a simulator that you can reset a bunch of times. So maybe we should allocate some effort in trying to understand the hardness of learning with these oracles as well.
And kind of interesting thing is that, like Peter's talk, like that W function is essentially changing that measure, and it empirically performed very well. So why does it? And I think kind of trying to find what is the ideal, or why ideal might be what Peter found, that would be interesting, I think.
So Gerger, coming back to your point, are you saying we should write down a white paper, things that deep RL practitioners are doing that theorists are not looking at?
Yes, sure. Yeah, I guess that would be a good idea to have like a list on both ends, right? Yeah, I guess that was actually going to be my next and maybe final question is like, what are these tricks that are being used in deep RL that are really not looked at by practitioners? So like, yeah, the replay buffer is one of these. Another thing that really puzzles me is this truncation idea in PPO, this proximal policy optimization algorithm. There, the entropy regularization part is, I would say, sort of well understood by now, but the truncation bit is not so much. So I'm just curious about like, what are your favorite hacks that you would want to see understood? Anybody feeling strongly about it?
Sure. Well, we've been pushing pretty hard the last year on combining unsupervised learning and reinforcement learning, and I think, what does it mean to combine them in the right way, have them, benefit from each other rather than, interfere. Kind of general multitask interference kind of problems could occur. So I think it's a lot of open questions there.
Yes, that's right. Well, I suppose like a lot of these, I mean, there are two categories here, right? One where you don't even know like what is the precise problem formulation or what is even the question to ask, right? Or another one where, well, there's like sort of a precisely formulated question, but like nobody ever really looked at that. And I guess maybe we have more of the first type in reinforcement learning. That's my feeling somehow.
There's a lot of empirical things that we don't understand that well yet in RL. The use of the experience replay buffer, I think, could use a lot of thought, but I suppose some of the offline batch RL stuff is getting us some insights somewhat into the use of the experience replay buffer. I don't have a great answer for you, Gergely, because I don't know actually that are used that seem to be important. Sometimes I assume that tricks that were added and they may or may not have been important. And so I suppose as time passes, the tricks that were important trickle out because they stay in the code. But I don't know which of the tricks were actually useful and which of the tricks just happened to be there.
Yeah. I'm puzzled by the same things as well.
I think a big one, I don't know if it deserves study, but it's distributed training. I mean, if you look at what most of these big projects are using, right, there's some amount of distributed training and there's some amount of maybe caching going on, right, where now it matters how fresh your policies are that you're collecting data with, and what is the impact of that on your, I was reading a paper recently that was pointing out that, for example, when you do prioritize replay, if you insert a new data point into the buffer and you didn't compute, you sort of make sure that you train it right away by setting the priority to maximum, that actually hurts performance quite a bit. Okay, so sure, like, so now you have to compute it ahead of time. In theory, it seems like a trivial operation to just say, do the right thing. But the practical reality is now, if you try to implement this one way or the other, it complicates things quite a bit. But at the same time, there might be algorithmic solutions that just require a little bit deeper thought. Just say, you know, this is how you would. One thing we don't do very well, I think, in RL is often to consider the runtime cost of some of these algorithms, right? And you know, Rich would love to hear their sort, but the reality is most of the algorithms that are getting used today are linear time algorithm, or sort of constant time per sample. So.
Yeah, so he must be satisfied with that. But I guess the problem is that
I have one for you also, Greg. This is not RL specific per se, but when people do ensembles, they just randomly initialize the network, and that's it. Whereas the theory of ensembling says that you should subsample, you know, different subsets. And there's a big, I mean, in practice, nobody does the subsampling thing, or it doesn't matter. And somehow, you know, I think that's an example of a big gap between theory and practice. That's very precise.
Right, yeah. And I guess, like, more generally, this belongs to this question of uncertainty quantification, which is apparently widely believed to be the key to do efficient exploration in reinforcement learning. Yeah, so of course, if you want to do it right, then you want to sample the weights from a particular distribution, you want to subsample, and then you want to make sure that you're sampling from the right posteriors and everything. Yeah, that was a bit of a discussion about that yesterday as well. Yeah.
And this is a very exciting segue to actually say that there will be a discussion about uncertainty again on Friday.
Wow.
For now, we should possibly wrap up since it's 3 o'clock.
Oh, yes. Right.
Gergely, maybe I'll let you say the final words on the discussion, and then I'll wrap up for the session itself.
Oh, no, I really just want to thank everybody for showing up and discussing so intensely. This was very interesting. So let's continue this, and I'm gonna start writing on my book of open problems for theorists and practitioners. So yeah, let's stay in touch regarding that. And now I guess it's time to head into this gather town thingy. I suppose there should be a link posted to that somewhere in the chat. So yeah, see you there. Thank you, everybody.
Thank you. Thanks to all the speakers today as well. Thank you, Gergely, for hosting the discussion, and see you again gather town tomorrow.
Thanks for agreeing to write 2 books, Gergely.
Thank you. Goodbye.
Thank you. Bye.
Thanks, everyone.
Thank you. Bye.